Okay, year 12. So this video will be looking at subtopic 3.9, which is about triglycerides. Now, the first thing we need to know about triglycerides is that they are made up of two main types of pieces put together. Now, the first bit is that it uses a glycerol, which is also, or the systematic name of that is propane 1,2,3-triol. It has, obviously, by the name, 3 hydroxyl groups. That piece is what bonds to fatty acids via an ester bond, or via 3 ester bonds to 3 fatty acids, to be more accurate, to give us our triglyceride or our fat or oil. Now, if we look here, you'll see a drawing of glycerol. So it's often drawn in this orientation, so up and down, with the OHs all coming off of one side. Now, it's usually done this way because the fatty acids they commonly join to are often long molecules, and if they were oriented up and down, it would take up lots of vertical space on a page. Whereas if it's left and right, it just takes up the line that you're writing on. Now, this shows us a connection or a esterification reaction that happens between this generic fatty acids with this R group on this carboxylic acid. Now we need to have, I know it doesn't actually say it here, but I'll put it here just there. So we need, for every glycerol, because it has 3 alcohol groups, OH groups or hydroxyl groups, we need to join it with 3 molecules of fatty acid. Now when they undergo that esterification reaction, we make 3 ester bonds between the glycerol and the fatty acid, and we also liberate a molecule of water for each ester bond that's been formed. In this case, it's going to be 3. This is pretty much the same chemistry that happens in the subtopic 3.7 esters. It just happens 3 times to 1 molecule. Now, what you'll need to be able to do is, if you're given the fatty acid, so the specific fatty acid with the specific R group, for example, down here we have hexadecanoic acid, which has 16 carbons in it. If you're given that, you need to be able to combine it with glycerol to make the resulting triglyceride. So in this case, we have our glycerol, we have our 3 times or 3 of our hexadecanoic acids, again in this case. We join them together, and I've also taken the liberty of highlighting the particular parts that are removed when the esterification happens. So we know it's a condensation reaction. We know that we're going to lose a water molecule for every ester bond that's made, and the OH comes from the carboxylic acid, and 1 hydrogen comes from the alcohol. And we end up making this structure here. So it's a specific triglyceride with a specific structure. Now, I can't remember. Actually, I think I'll write it down a bit further, the particular name. So, I'm not exactly sure what the resulting triglyceride would be called in this case, but you don't need to be able to name them. If they give you a structure with a name, that's great, but you would never have to name them. So, we've shown so far the joining between carboxylic acids to alcohols to make our fatty acid, but you'll also need to be able to break apart a triglyceride if given its structure. So you need to be able to break it into the pieces that make it up, which, again, I've taken this same triglyceride with the hexadecanoic acid parts to it, and it undergoes hydrolysis just as happens in the ester subtopic. We add 3 molecules of water because we're breaking 3 ester bonds. We're cutting them in here, adding a hydrogen to one side and the OH to the other. And we'll liberate an alcohol, so the glycerol in this case, which is that propane 1,2,3-triol. And we'll liberate 3 molecules of our hexadecanoic acid. Now, as per the ester section, if the hydrolysis reaction is done in an acidic environment, then you're going to end up forming the carboxylic acid, like the fatty acid, so the carboxylic acid version of the fatty acid. If instead you do it under basic conditions, the acid will act as an acid, lose the proton, so this particular one here, and will end up as the carboxylate ion version of the fatty acid, which is shown generically here. So it's the exact same concept as in the ester section, as well as amine section, which, the amine section in 3.6, actually I said 3.8 before, but that's amines. Either way, now that we've looked at the structure of them and how they join together and break apart, we are going to look into a little bit more detail of the fatty acids themselves. Now, fatty acids have a particular property called saturation. Now, saturation describes the makeup of the fatty acids themselves. So, if we look along this fatty acid, so this is tripalmitin. So, each of the fatty acids are called palmitic acid, and as you can see, there are no double bonds along this carbon chain. Obviously, you've got the double bond here with our oxygen, but that is not what we're talking about. We're talking about double bonds between carbons. Now, when you have these triglycerides, first things first, you can look at the saturation, which means how many carbon-carbon double bonds they have. If they have none, they are what's called fully saturated. If you were to try and react this molecule with hydrogen, so hydrogen gas, which normally undergoes an addition reaction with alkene molecules. If no reaction will occur, it's fully saturated. If you put the hydrogen in and it'll essentially absorb or react with it or add to it, then those fats were unsaturated. Fatty acids also have another characteristic, which is size, and similar to our hydrocarbon section. Actually, no, I don't think we did one. Either way, similar to hydrocarbons, the dispersion forces will increase with the size of them. Now, these dispersion forces increasing make their melting point higher. Our molecules being saturated also tends to make their melting points higher and makes them more likely to be fats as opposed to oils. Fats being solid at room temperature. Now, the reason for that is because of the way these are structured. They are able to sort of, one triglyceride and another triglyceride can sort of arrange themselves and overlap more easily, which increases the dispersion forces between them. And so increasing those dispersion forces, increasing the intermolecular forces, will increase the melting point of those. So for this particular one here, we have a melting point of around 66 degrees Celsius. Now, if we look at a different one, so in this case, we have triolene, which is made up of glycerol with 3 oleic acids. You'll see the glycerol part, the backbone here, is drawn quite differently. Now, the reason for that is because the fatty acids themselves, they have this double bond structure, and they bend. So this bend means that I can't just draw them all in a straight line like this, because otherwise, they'll sort of kink over on top of each other. So instead, you can rotate these bonds around a little bit to show it drawn like that. Pretty much, you will not have to. Pretty sure you will not have to draw anything like this that's this complicated and this bent. But just don't be surprised if you see it. So you can still see the 3 carbons, the propane. And there's the 1, 2, 3 triol. So you've got those OHs, or what used to be OHs, hanging off those 3 carbons. Now, just as an aside, I don't think I've mentioned it here, but you may have heard the term trans fat being thrown around before. So they are typically considered to be sort of a more unhealthy one. So these ones here, when they have a double bond, if they bend, because these bonds here are on the same side of this double bond here, they are cis fats. They're not trans fats, and they are generally fine. So actually mostly considered healthier versions of fats. When they continue their structure like this because they're on opposite sides of this double bond, so one on this side and one on this side, they actually mimic these saturated fats in shape, and then they sort of insert themselves into places that they shouldn't be, and even though they behave a bit differently. So pretty much not a big deal. All you need to really know is that these ones here, because of the bent structure, they don't really overlap very well, and they don't have strong dispersion forces between other triglycerides or other molecules, which lowers the strength of the intermolecular forces and decreases their melting point. So in this case, we have our melting point of trioline as 5 degrees Celsius, which is much lower than our 66 degrees for our tripalmitin. These, just again another aside, these single bonds, they all can rotate around, so they can all flop around everywhere, but they'll tend to overlap and straighten out when the need suits them. The unsaturated, though, when you have a double bond, they can't bend at that point, so they are that particular part is rigid. So there can be some bending happening here, there can be some bending happening there, just as I've shown down here, but at that particular spot, it's rigid. It can't change its structure. Now, all of these examples of triglycerides that I've drawn, I've shown you 3 of the exact same fatty acid joined to the glycerol. That is not necessary. So I've done it for simplicity's sake, but you can get, you do get combinations of 2 or 3 different types of fatty acids attached to one glycerol molecule. And when you do attach different types, so you might have one saturated fatty acid, one unsaturated with just a single double bond, and then one with multiple double bonds. When that happens, then the properties of that triglyceride will be sort of like a sum of all the bits that make it up. So if it's more saturated, it's going to have a higher melting point. If there's middling amount of saturation, its melting point's going to lower a little bit. If there's lots of unsaturated parts, then it's going to have a lower melting point and be more likely to be an oil as opposed to a fat. Now, the level of unsaturation does vary as well. So we've obviously got none here, and we've got one double bond in each of these fatty acids here, but you can get up to 6 double bonds in one fatty acid. So one of these things will have up to 6. An example of that is herring acid, which herring being the name of the fish that this acid comes from. But yeah, so you can get no saturation, mono unsaturated. Then you have polyunsaturated, where there's 2 or more, up to 6 or so double bonds in each fatty acid molecule. So we can get a rough idea of the saturation by looking at the melting point of a substance, but because of all the different combinations of saturated and unsaturated you can get, it doesn't make it very easy to actually determine the saturation level. So instead, we can do it chemically. So we can work it out by reacting these triglycerides with molecules that we know will react with the double bonds. Now, that can be, commonly it's going to be diatomic molecules such as I2 or Br2, so iodine or bromine. It can also be, you can also react it with something like, chlorine, diatomic chlorine or diatomic hydrogen, but commonly it's done with iodine and bromine, mainly because of, the color of these molecules here. When it reacts, the color of that molecule disappears because that molecule is gone now, and it gives a nice easy way to be able to determine whether the reaction has happened, because your colored substance you put in is used up and it remains colorless. Either way, it's a simple addition reaction that happens between these diatomic molecules and the double bonds, the carbon-carbon double bonds in these unsaturated fatty acids. And each instance of a double bond in these fatty acids will react with 1 mole of our gas. So if we have 1 mole of fatty acid with 1 double bond, that's essentially 1 mole of double bonds, and so it'll react with 1 mole of our diatomic molecule, so our bromine, for example. in this example here, we have triolene, and that's the one from up here, where one molecule of triolene has 1, 2, and 3, 1, 2, and 3 carbon-carbon double bonds. So that means if you were to fully saturate it, for every mole of triolene, you'd react it with 3 moles of bromine, and that gives us a molar ratio of 1 to 3. Now, I've given a bit of an example down here. Now, even there is something called a bromine number, which is analogous to an ID number, but you generally hear of ID number more commonly. So that's the one example I'm going to use here. So the ID number, what it means is if we have 100 grams of whatever oil or fat we're looking at, this tells us how many ID number is the number of grams of iodine that reacts with that, fully reacts and fully saturates that 100 grams of oil. Now, 100 grams of each oil is a different number of moles of each oil, based on obviously the molar mass of that substance. So we're going to do an example here to hopefully explain that a bit better. So if we look at linoleic acid, so linoleic acid is sometimes referred to as C18-2. Now, C18 tells you how many carbons there are, and so before I continue, I'm going to make a bit of a distinction. So you can react it with the oil or the fat, so the triglyceride, but you can also do these reactions with the free fatty acids. So imagining if the ester bond was broken, the ester bond was broken and you've liberated all of the fatty acids. So this example is going to be done on a free fatty acid, which again, in this case is linoleic acid. It's called C18-2, and that means it's got 18 carbons and 2 carbon-carbon double bonds in it. So this means the molar ratio of the acid to iodine, when they fully react and fully undergo an addition reaction, will be 1 to 2. So 1 mole of linoleic acid will react with 2 moles of our diatomic molecule, in this case iodine. So when we look at our calculation, we have the mass of our linoleic acid. Now, when we're trying to calculate the ID number of that substance, you have to have 100 grams of it. The molar mass of linoleic acid, you can either calculate it from its structure, or you might be given the number. Regardless, it is 280.45. So we can calculate from the mass and the molar mass, we can work out the number of moles, and for this molecule, it is 0.357 moles. Now we know the number of moles of iodine that will fully react with that will be twice that number. So we have 0.357. The number of moles of iodine is twice that, because we know that you need 2 molecules of it to react with 1 molecule of fully react with 1 molecule of linoleic acid. So we multiply that number by 2, and we end up with 0.713. Now, just a heads up, I have the numbers I've written here rounded, but the calculations I did were not rounded, which is why this number and this number are not direct factors to each other. Now, we know the number of moles of iodine. We also know the molar mass of iodine from the periodic table. It's twice the number of moles of iodine atom by itself, and that is 253.8 grams per mole. Now, knowing these two numbers, the number of moles and the molar mass, we can use the rearrangement of our mole equation, which is mass equals number of moles times molar mass. 0.713 times 253.8 gives us 183 grams of iodine that will react with our 100 grams of our fatty acid. So that equates to an iodine number of 181. If we were calculating something else like a bromine number, then the calculation will be essentially identical. The difference will be this bit here, where so the number of moles of bromine would be the same. It'd be the double, because again it reacts the same way as iodine, but the molar mass of bromine would be different, which would result in a different mass of bromine. Okay, so we've been going for a while now, but we'll keep going. We shouldn't have too much left, hopefully. Now, if we mentioned earlier that saturated fats have a lower melting point. So if we have so they're more likely to be more like oily or liquid at room temperature. If we have unsaturated fats, so ones with double bonds that are, what have I done? Sorry, I know I've made a mistake. I've caught myself. when you have a saturated fat, all the bonds are single bonds. They can overlap. They can align themselves straight. They can overlap quite well, and their intermolecular force is stronger, which means their melting points are higher. So saturated fats have higher. Now, unsaturated fats, such as oils, like for example, ones that end up like classed as oils, which means they're liquid, they can be converted into fats, so converted into saturated fats, where their double bonds have been saturated and they've got no double bonds anymore, via a reaction with hydrogen. So we call this being hydrogenated, and essentially you convert the double bonds into single bonds. Now, there are some steps that need to be taken, because this reaction, if I just put a unsaturated triglyceride in a container with some hydrogen gas, the reaction would essentially not happen. It'd be so slow that it might as well not be happening. So what we do is we use pressure, temperature, and a catalyst to increase the rate of that reaction. So we've done it, we've looked at it before, but essentially, super briefly at least, we have pressure. If we pump in heaps of hydrogen, increase the pressure of hydrogen in the reaction container, you're going to get more collisions happening between hydrogen and the saturated fats. The unsaturated fats. I keep making that mistake. Sorry. You get more hydrogen molecules interacting with the double bonds of the unsaturated fats, so you get more collisions and obviously more successful collisions. Now, temperature. Temperature, same as usual. If you increase the temperature, you increase the amount of energy that the reactant particles have, which increases the proportion of successful collisions that occur. Now, we're not talking about equilibriums here, we're just talking about reaction rate. So temperature, increase it, reactions happen faster, and that's what we want, because the reaction was very slow to begin with. Now, I've said it here as a little note that these are exothermic reactions, these hydrogenations. Now, being exothermic, if we do increase the temperature, it does push the equilibrium position backwards towards the reactant. But the point is that if we don't increase the temperature, then you're not going to get any products at all, because it's so slow. So if we increase the temperature, at least it can happen quickly enough for us to be able to use this stuff. Now, the last one is use of a catalyst. So using a catalyst, if they often will use a metal such as nickel, but this reduces the activation energy. Same stuff we've learned before, increases the number of successful collisions because they don't need as much energy anymore. Okay, so I just as an aside, this is how they often make margarine. So margarine is what they get when they hydrogenate unsaturated oils and essentially turn them into fat. So you take a plant oil, you hydrogenate it, it turns it into a fat. Okay, so pretty much near the end now. We have a little bit more detail on what happens when we change the conditions of hydrolysis of these triglycerides. So if we take the triglycerides, we hydrolyze them, split apart the ester bond. If we do it in an alkaline condition, which is another word for basic conditions, we produce these carboxylate ions. So again, just like I mentioned earlier. Now, the important reason we are looking at those is because that carboxylate ion, like we talked about in the carboxylic acid section, interacts with water more strongly than the carboxylic acid part. So because we have our carboxylate ion area, which has our oxygen, 2 oxygens, and our negative charge, this negative charge gives it a more like a stronger, instead of it being a dipole-dipole interaction or even a hydrogen bond with water, it becomes an ion dipole bond with water, which is stronger. So when we do it as base, we end up with our hydrophilic region, our region that will interact with water favorably. We also have this long chain of carbon, and carbon-hydrogen bonds, and that, as we know, only has dispersion forces and does not interact favorably with water. What we can do is we can illustrate that as our little hydrophilic head and our hydrophobic tail. So you might have seen this stuff if you in biology, for example, but for chemistry purposes, the important bit, as I said, is that the carboxylate ion has a strong interaction with water on that hydrophilic end. And what that means is you can take all these carboxylate ions and you can arrange them in sort of a sphere. So I've drawn it in 2 dimensions here, but you arrange them in a sphere where on the outside of that sphere you have our hydrophilic ends. So those are going to be on the outside because that means they're going to be interacting with the water that's surrounding them. On the inside, we have all these hydrophobic tails, which all have dispersion forces and all are happy to interact with each other. Not only are they happy to interact with each other, but they're shielded from the water. They're not interacting with the water, which makes it a good interaction as well. So these little things, these little structures, these little bubbles, or if you think of them like that, they're called micelles. So micelles are important because they can carry within that hydrophobic area any sort of non-polar molecules of interest. So you could use these to carry, hydrophobic drug molecules to a particular place in the body, or more day-to-day example would be for soap. So that's the last thing I'm going to mention here. Soap is, when you're using it, it forms micelles. What it does is these little droplets, these little micelles will essentially dissolve or disperse in water. And what they'll do is they'll carry around these non-polar molecules. So for example, dirt or grease. And that means that they can be carried around throughout the water by these micelles. Normally, if you try and put water on, let's say, an oil or a grease, it'll just won't dissolve it at all, and it'll leave it exactly where it was, on your hands or wherever, or on clothes. If you have these micelles, they will take it within them, and then they'll float. They'll rinse away with the rest of the water because these bits here will, happily float around and essentially dissolve in the water. And I think that's pretty much it. So we've talked about triglycerides, we've talked about what makes them up, we've talked about how we can split them up, and then we've taken that splitting up in a particular way, the alkaline hydrolysis, and we have looked into a particular use, such as soap. So I hope that helps.